Module 9 Cross-sectional Studies. As demonstrated in the schema of categories of study designs, a cross-sectional study is an observational epidemiologic study that can either be descriptive, that is exploratory or hypothesis generating, or analytic, that is when a predetermined hypothesis is being tested. Often, cross-sectional studies capture both descriptive and analytic components. In cross-sectional studies, one observes a sample of the population at a single point or over a brief period of time. A key feature of this design is that the study group is not recruited based on a specific characteristic of interest, but rather they are selected so that they are representative of the whole population, so that information collected can be generalized directly to the whole population. Cross-sectional studies are conducted to collect information on any aspect of health or lifestyle. The most commonly used survey methods include interviews either in person or on the telephone, questionnaires, and physical examinations. The exposure and outcome are assessed at the same time, and because exposure and outcome are determined simultaneously, it can be difficult to identify which came first. Therefore, it's not always easy to interpret cross-sectional data in causal terms with respect to disease etiology. The individual level data obtained is analysed descriptively to estimate prevalence rates, evaluate knowledge or attitudes towards disease and health, or the analysis may be analytic, involving the calculation of odds ratios or prevalence ratios in order to describe the association between exposure and disease. In summary, data is collected on a representative sample of the population, with exposure and outcome being ascertained at the same point in time. Participants are then categorized by their exposure outcome status to calculate a measure of association and evaluate the relationship between exposure and outcome. The strengths of cross-sectional studies are that they are relatively quick and easy to undertake, they're economical, as no follow-up is required, they're representative of the population, and data can be collected on multiple exposures and outcomes in a single survey. Therefore, data can be used in multiple ways. The weaknesses are that they cannot establish temporality, and as you recall, this was a necessary criteria in assessing causality according to Bradford Hill. As prevalent cases of disease are identified, samples overrepresent conditions with longest duration. It is difficult to study rare diseases as the sample size required to identify adequate cases would not be practical. And finally, it's difficult to study past exposures in relation to current outcomes, especially when onset is uncertain. National cross-sectional studies, such as the Canadian Community Health Survey, are carried out at regular intervals. These surveys reveal changes in the population prevalence of disease, disability, and risk factors over time. The Canadian Community Health Survey, or CCHS, is a cross-sectional study that collects information related to health status, health care utilisation, and health determinants for the Canadian population. It's a joint initiative led by the Canadian Institute for Health Information, CIHI, Statistics Canada and Health Canada, and has the following objectives: to support health surveillance programs by providing health data at the national, provincial, and intra-provincial levels, to provide a single data source for health research on small populations and rare characteristics, to ensure the timely release of information easily accessible to a diverse community of users, and finally to create a flexible survey instrument that includes a rapid response option to address emerging issues related to the health of the population. When it first started in 2001, data was collected every 2 years, but since 2007, data has been collected annually, with 65,000 individuals over the age of 12 years living in the 10 provinces and the 3 territories invited to participate. If you or a friend or relative have participated in the CCHS, please post about your experiences in the modules discussion forum so we can all hear more about it. We will use a research project based on data from the CCHS entitled Beverage Patterns Among Canadian Children and Relationship to Overweight and Obesity to highlight the steps to conducting an analytic cross-sectional study. This paper has been posted on Blackboard for your review. The first step in designing an analytic cross-sectional study is to develop a hypothesis or articulate a study question. In this study, the authors wanted to know if the consumption of sweetened beverages was associated with overweight or obesity in Canadian children. In the background of the published paper, the authors explain that the observed rise in childhood obesity has also been paralleled with an increased consumption of sweetened beverages by children. And as these beverages have little nutritional value and do not provide satiety, there is rationale to suggest that they can cause weight gain and obesity in children. The second step is to define and select the target population and draw a representative sample. The current study focused on a subsample of the CCHS 2.2 respondents from 2004, namely almost 14,000 children aged 2 to 18 years. This sample was using a multi-stage stratified complex survey design where specific geographic areas are identified for sampling, then a list of dwellings are sampled from that area, followed by selection of one person per household being selected for the survey. The survey excluded those living on First Nation reserves, members of the armed forces, and those in some remote areas. The overall response rate to the survey was 76.5%. The third step is to use reliable and valid methods to measure the exposure and outcome of interest, plus potential confounders. In this example, the exposure was sweetened beverage consumption. In the CCHS, trained interviewers use a standardized computer-assisted interviewing technique to collect data directly from the respondents, or parents in the case of children under 12. Detailed information on the food and beverages consumed in a 24-hour period was collected. The amounts consumed were converted to grams. The authors then categorized the type of beverages according to their energy and nutrient content, namely sugar-sweetened low nutrients, such as fruit drinks, soft drinks, sweetened coffees and teas, nutrient-based, for example, plain milk, milk-based beverages, and no-calorie, such as water, diet, soft drinks, and unsweetened coffee, tea. Finally, the authors completed a cluster analysis, a statistical approach to grouping data so that items within the same group are similar, which enabled them to classify children by their dominant pattern of beverage intake, namely soft drink, fruit juice, milk, high fat, and moderate. In the moderate group, no single beverage type was consumed in greater quantities than others. These multiple stages to determining a child's beverage pattern illustrates that the epidemiologist's job of acquiring the data is not always straightforward. The outcome of interest in this study was overweight and obesity. Thus, interviewers measured the height and weight of children using standard procedures. Based on these heights, weight, and the age of the child, their body mass index for age was calculated, and established cutoffs were used to classify each child as normal, overweight, or obese. Once measured, a statistical analysis was conducted to evaluate the association between exposure, beverage consumption, and outcome, obesity. After excluding implausible measurements, the authors analyzed data on 10,000 children. The analysis was stratified by age, 2 to 5 years, 6 to 11 years, and 12 to 18 years, and sex for children greater than 5. Chi-square tests and logistic regression were used to evaluate the odds of being overweight obese in children with a dominant beverage consumption pattern compared to children with a moderate beverage pattern. In the logistic regression models, this association was adjusted for potential confounding variables. Overall, no sweetened beverage cluster was significantly associated with overweight obesity across any of the age groups after adjusting for various confounders, with the exception of soft drink consumption in the group of 6 to 11-year-old boys. Let's take a step back for a moment and reflect on how the authors arrived at these conclusions. We will refer to a 2x2 contingency table for calculating prevalence rate ratios and odds ratios. For our purposes, we will focus on the 6 to 11-year-old males group, but you could repeat this with any of the strata. From Table 1 in the published paper, we see that 219 boys had a high intake of soft drinks and 630 had a moderate intake of all beverages. From Table 2, we see that 47.5% or 104 boys in the soft drinks group were overweight or obese, and 25.3% or 159 boys in the moderate group were overweight or obese. From this, we can calculate that the prevalence of overweight obesity was 104 over 219, or 47.5% amongst soft drink consumers, and 159 over 630, or 25.2% amongst moderate beverage consumers. So this indicates that the prevalence of soft drink consumption is almost twice as high amongst overweight obese boys compared to normal weight counterparts, with a prevalence rate ratio of 1.88. Using the 2x2 table, we can also calculate a crude odds ratio of 2.68. The adjusted odds ratio in the published paper is slightly attenuated at 2.28, with a 95% confidence interval of 1.2 to 4.1 that does not straddle 1, indicating significance, which is corroborated by the statistically significant p-value of 0.07. This means that boys aged 6 to 11 years who predominantly consume soft drinks are 2.3 times more likely to be overweight or obese than boys who consume a moderate amount of all beverage types. However, given that this association was not replicated in girls or in other age groups, I would conclude that the evidence to support the hypothesis is weak, and this observation may be spurious due to multiple testing. But it would be great to hear your thoughts on this on the discussion forum on Blackboard. When assessing the validity of this study and cross-sectional studies in general, the potential sources of bias are associated with sample selection and measurement of the exposure and outcome. If specific groups are excluded, such as those living on First Nation reserves, families in the armed forces, and in remote areas in the CCHS, then it can raise doubt over the representatives of the sample. However, Stats Canada has estimated that using the complex multi-stage sampling strategy, the CCHS is representative of 98% of the Canadian population. A poor response rate may also indicate a selection bias when individuals who respond differ systematically from non-responders. For example, they might be more interested or knowledgeable about health. In the CCHS, the response rate was 76.5%, which is adequate. There may also be biases associated with reporting of beverage intake, such as poor memory or recall, especially as the survey was completed by the parents for younger children, and they may not be aware of all the beverages the child consumes external to the home. Also, they may have overreported perceived healthier beverages and underreported unhealthy high sugar beverages, a so-called social desirability bias. There may also have been some measurement error due to differences in how interviewers measured the heights of children or the calibration of weigh scales. However, the authors excluded children whose data was implausible. We'll be learning more about biases in the next lecture on case control studies. To conclude, descriptive cross-sectional studies provide a snapshot of disease and health. Analytic cross-sectional studies provide preliminary evidence about many hypotheses in one study. Temporality is a major concern of cross-sectional studies.